Good evening. So last class we have seen about uniform convergence and continuity. So we have completed that, and now we are going to see about uniform convergence and integration. So relation between sequence of functions which are integrable functions and the uniform convergence of that. Okay. So there is a theorem on that. So this theorem gives you the answer for the question we have in the beginning. Okay. So consider a sequence of functions where all Fn are Riemann Stieltjes integrals. Okay, alpha is monotonically increasing. Those things are there. Okay, from Riemann integration. So recall the Riemann integration and do this. Okay, so Fn belongs to R of alpha on AB. Okay, this is the sequence of Riemann integrable functions, and Fn converges uniformly to F on AB. Okay, the convergence is uniform. If that is there, if this happens, then F is also Riemann integrable, Riemann Stieltjes integrable, and the integration, the integral a to b f d alpha is nothing but limit n goes to infinity, integral a to b fn d alpha. Okay, that is, the limit inside can be taken out, or this can be written as integral a to b limit n goes to infinity f d alpha fn d alpha is equal to limit n goes to infinity integral a to b fn d alpha. Okay, so like this. So we have to prove two things. One is f is Riemann integrable, and the other is this integration. Okay, so we shall prove that. So we know that fn is Riemann integrable, and this convergence is uniform. Okay, so convergence is uniform means we can speak about this fn of x minus f of x. Okay, in the interval R, take the supremum of this in the interval AB. Okay, call this as Mn. Mn is supremum of mod Fn of x minus f of x. Okay, this we know. Since Fn converges uniformly to f on AB, since this is there, Mn converges to 0. Okay, Mn converges to 0 as n goes to infinity. Okay, this is the result in our uniform convergence. Okay, so go through that. So this Mn converges to 0. Now we have to get the relation between this. Okay, see here, this is the supremum of this. So we know that supremum is always greater than or equal to each of those elements. So this we have mod Fn of x minus f of x is less than or equal to supremum. So supremum means that is Mn, correct? Mn for any x in AB, correct? For any n, correct? This is true, and this can be written as minus Mn less than or equal to Fn of x minus f of x less than or equal to Mn, which is, so I want f of x here and Fn here. Okay, so I'll take this plus minus. Okay, so add Fn of x everywhere. So we will get Fn of x minus Mn less than or equal to f of x less than or equal to f of x Fn of x plus Mn. This is true for any x and for any n. Okay, we have this. Since or this can be written as functions alone, Fn minus Mn less than or equal to f less than or equal to Fn plus Mn. We know that Fn, since Fn belongs to R of alpha, this implies Fn belongs to R of alpha and Mn also belongs to R of alpha. So Fn minus Mn, Fn plus Mn, all are elements of R of alpha. Right? All are Riemann integrable functions. Mn is just a real number, so that is also Riemann integrable. Okay. So these two are Riemann integrable. So integral a to b Fn minus Mn d alpha also plus or minus, both exist. Okay, so no need to worry about that. Okay, so consider that integration. So consider that integral a to b fn minus mn d alpha, this integration. Right? What is the definition of that integration? Either upper sum or lower sum, with upper sum or lower sum. So we can consider with the upper sum. Okay, so upper sum means u of p fn minus mn alpha. So upper sum means what this will be? Infimum, correct? Infimum over the upper sum, infimum over the partition. Okay, and this will be always less than or equal to infimum of p u of fn is less than or this is less than or equal to this. So lower sum is less than or equal to lower sum. Okay? So we will take that lower sum. Supremum over the partition lower sum L of PF alpha. Okay, L of PF alpha PFN minus M1 comma alpha. Okay. So this is less than or equal to supremum of L of PF alpha. Correct. What is this? This is your lower integral. This is equal to the lower integral f d alpha. Correct. Lower integral. We don't know whether f is integral of that or that's what you have to prove. Okay. So we have just wrote a integral lower integral a to b f d alpha, which is always less than or equal to what? Upper integral f d alpha, less than or equal to the upper integral. Okay, and which is equal to what? Infimum over u of p f alpha or the partition, and f is less than or equal to fn plus mn. Correct. So this is always less than or equal to infimum over the partition u of p fn plus mn alpha, which is nothing but upper integral. Sorry, not upper integral, just integral, because that is integral. Fn plus mn. Okay. So what you have found? Integral a to b fn minus mn d alpha is less than or equal to integral lower integral f d alpha less than or equal to the upper integral f d alpha less than or equal to the integral fn plus mn d alpha. Clear? This we have found. Clear? Now we'll use this to prove that f belongs to R of alpha. So f belongs to R of alpha means what do you have to prove? We have to prove that these both are equal. Correct? These both are equal, we have to prove. Fine. So consider that 0 less than or equal to upper integral minus lower integral. Consider this. That both are greater than or equal to, so differential. Okay. And this is, we know that this is less than or equal to, this 2 is less than or equal, upper integral is less than or equal to this integral a to b fn plus mn d alpha minus of this is less than or equal to minus of this. So integral a to b fn minus mn d alpha, which is integral a to b fn plus mn minus fn plus mn d alpha. Okay, which is equal to 2 times integral a to b mn d alpha, which is 2 times mn alpha of p minus alpha of a. Correct. We know that this goes to 0 as n goes to infinity, since mn goes to 0 as n goes to infinity. Okay. So what we can do? These both are equal. So which implies integral a to b f d alpha is equal to integral a to b f d alpha. Lower integral is equal to upper integral. This implies f belongs to R of alpha. Okay. Then star implies this inequality what we have got? Integral a to b fn minus mn d alpha is less than or equal to the integral itself is less than or equal to integral a to b fn plus mn d alpha. Clear? Now, so simplify this. This implies integral a to b fn d alpha minus integral a to b mn d alpha less than or equal to integral a to b f d alpha is less than or equal to fn d alpha plus, which implies minus m times alpha of b minus alpha of a, this less than or equal to integral a to b f d alpha minus integral a to b fn d alpha less than or equal to m times alpha of b minus alpha of a, which is nothing but modulus of integral a to b f d alpha minus integral a to b fn d alpha not mn, okay, which is less than or equal to mn times alpha of b minus alpha of a. This goes to 0 as n goes to infinity, correct? Because of this. This implies what? As n goes to infinity, integral a to b f d alpha is equal to integral a to b fn d alpha. That means what? As n goes to infinity can be replaced by limit n goes to infinity, this system. So this is what we have. Okay, so we have got that. So now there is a corollary for this. Corollary is, here we have done with sequence, so there we will do with series. Okay, so let f of x be summation fn of x, where each of the fn are Riemann integral functions. If this is there, if this series converges uniformly, then f belongs to R of alpha. Okay, if the series converges uniformly, then f belongs to R of alpha, and integral a to b f d alpha is nothing but limit n goes to infinity integral a to b Sn d alpha. Okay, that is that. So this is just direct consequence of your previous theorem. So what you have to do is, only thing is, let Sn be nth partial sum of that series fk of x. Okay, we know that each of the fk are Riemann integrable. So sum of Riemann integrable functions are Riemann integrable. So this implies Sn is also Riemann integrable function. Correct? Sn is also Riemann integral function. And we know that Sn, this converges uniformly to f. That means this implies Sn converges uniformly to f. Correct? Sn converges uniformly to f, and each of these are Riemann integration. So by previous theorem, this implies f belongs to R of alpha. That's all. Okay. And integration also. Integration follows from this. So we know that integral a to b f d alpha is equal to what? By previous theorem, is equal to limit n goes to infinity integral a to b Sn d alpha if there is a sequence Sn Fn. Okay, and what is Sn? Limit n goes to infinity integral a to b. Sn is this summation k from 1 to n Fn of x d alpha, and summation, if that is finite series, we can take it out. Okay, so finite series and integration can be replaced. So this is limit n goes to infinity, summation k from 1 to n, integral a to b, fn d alpha, which is nothing but summation n from 1 to infinity, integral a to b, fn d alpha. Here it is k, there it is n. Okay, so we have proved that integral a to b f d alpha is equal to summation n from 1 to infinity, integral a to b fn d alpha. Okay, so sorry, here it is fn, not s. So this is also equivalent to say that integral a to b summation fn n from 1 to infinity d alpha is equal to summation n from 1 to infinity integral a to b fn d alpha. Okay, see this, what is happening there? We can shift the integral and the summation whenever the convergence is uniform. Right? So that's what the conclusion from this theorem. Okay, so integral sign and the summation can be replaced if the convergence is uniform only. Okay, that's so this is about your uniform convergence and integration, and there is some examples for this theorem. So just go through that. Example is this. So this n square x into 1 minus x square to the power n, and cos m factorial pi x to the power 2n. These two sequences are there. So this two sequence converges pointwise but doesn't converge uniformly. So because of doesn't converge uniformly, this inequality will not be true. This inequality will not be true in the case of these two sequences. So you can go through that and work it out and see. Work it out. So find the integration for both the things and verify this. Okay. So this left to you as exercise. So this is about your uniform convergence and integration. So we will see the uniform convergence and differentiation in the next class. Okay. Thank you.